Okay, good afternoon, everybody. Okay, let's see what's going on here. Doesn't seem to want to do that. Okay, so good afternoon. What's happening here? Should be okay. All right, so give me a like to see if you can hear me. Hopefully you guys can hear me here. Okay, got the likes coming in. Okay, so let's remark about a few things here. I know what's happening. It's my keyboard. There we go. Okay. Sorry about that. Just trying to get squared away out here. So, all right, let's go to the browser here. Let's see a few things. I'm going to check our internet speed. Hopefully we'll have some good speed. We had some good speed this morning. And that's very good download speed. Let's see what the upload speed is like. So the upload speed is very good as well. So set your YouTube to HD, and you can maximize your experience in HD. Hopefully you guys do that. So we're good there. And let's also double check what's going on here with this class, right? So we know that our test 4 is a take-home test. We talked about that last week. And go down here. Now, some of you guys may, go to this class and this website and you go, I don't see it. I don't see it. Well, hit refresh on your browser. If you hit refresh, click on that, and you're going to see a test 4 here. And here it is. Here's test 4 for you guys. So there's some questions that we've worked on in class, okay? And this test 4 is a good it's a good review. You can put your answers sheet in the answers portion as well. And that's going to be due the day of your final. So if we look at the schedule, we can say, okay, when is that due? That's due December 15th, right before class, 9:30 a.m. So this take-home test 4 is due next week on Tuesday, December 15th. So ladies and gentlemen, that's how things are transpiring here. So there you go. And I just want to remark about that. It's already in Canvas. It's already on my website. So I communicated all this stuff with you guys this weekend. So hopefully you guys have gotten started. I think somebody has already turned it in, by the way. So somebody was done with this. So good for that person, whoever that person was. So somebody turned it in already. So let you guys know. We're going to continue with Okay, thank you, Nick. We're going to continue our work with polar curves. Now, polar curves, ladies and gentlemen, or polar coordinates, you might think of this as here's our polar axis, right? We have our pole, and what we already talked about is you can superimpose the Cartesian coordinate system over this polar axis. And what you have here is a relationship between the Cartesian coordinate system and the polar coordinate system. And we converted points last week. Now, remember the key ideas that we used was that x will be r cosine theta. We know y is r sine theta. We know x squared plus y squared is r squared. And we know that tangent theta is y over x when x is not equal to 0. So we used this information last week. Okay, so here's kind of where we're at. And I want to remark here that there's something called a polar curve, where r is a function of theta. Very much like in Cartesian coordinates, y is a function of x. So this is in Cartesian coordinate, and this is in polar coordinates. Okay, so there's a relationship between the two. Now you might say, why do I have to study polar coordinates anyway? Can I just stick with Cartesian coordinates? Well, for a lot of things, that's a lot of curves that you guys see in Cartesian coordinates, polar is easier to describe the curve. You may not think it is, but it actually is. For example, if I said to you, let me go with, I got to be careful here. Let's move this stuff out of the way. For example, I guess the best example to give you, I'm not sure if your book does it, but your book does kind of an example. Let me be careful here. I'm going to look at this. I'm going to look at what we call a cardioid. And what I'm going to do now is introduce you to, let's go to our worksheets and videos. Let's see what we have there. Let's go to the browser. And I have this introduction to polar coordinates. We got to find that there. I see. I think I know. We're going to put polar coordinates, Daniel Judge. All right. Polar coordinate conversion. That's what we got here. I got intro. Oh, that was 3 years ago. All right. I'm going to have to update my website. Remind me to do that, you guys. Here we go. Got some polar work we're going to. Oh, yeah. This is calculus of polar curves. Okay. Well, anyway, let me look at this here for you guys. This is about an hour long we're looking at. Okay. Just going to do a few things here. Anyway, this is kind of what we're looking at. So that's a rose, whatever. Okay. Well, I'm going to do something a bit different for you. Let's go to the browser here, or the iPad, and I'm going to do this. I'm going to introduce you to a cardioid. Now, your book doesn't have a lot of this detail, which is kind of unfortunate. So let's go to the browser. We're going to look at some of these shapes here. This is called a cardioid, ladies and gentlemen. And cardioids have a lot of uses. They show up, in a lot of different places. Here's a cardioid. Here's how you kind of describe them. The graphs. But if you want to know what a cardioid is, it's a heart. So we can think of that cardioid as a heart. And here's kind of the general way we describe cardioids. And this gets a bit complicated. This goes into the area of calculus. You don't have to worry about that now. You guys aren't there yet. But let me actually do something here where I give you the fundamental definition of a cardioid, or at least give you an equation here to start working with. Cardioids. And you got cardioid, a math curve, so that's not what we're looking for. I'm going to look for my cardioids over here. All right, I think I know where I'm going to go. Let's go back to something like this. Let's go to the calculus, maybe. 261. And maybe calculus 2. It's calculus 1. How would we do a calculus 2? And I should have polar curves here. Yeah, here we go. All right, let me show you this cardioid. It's an upside down cardioid, by the way. So here's kind of what I want to describe here. It's not the general definition of a cardioid, but a cardioid is a curve. And we're going to say, for example, r equals 1 plus sine theta is actually, the equation of this particular cardioid that I'm looking at. And this is in the world of polar curves. So I go back to the browser. You say, wow, r equals 1 plus sine theta. So yeah, that's the cardioid. We're going to learn how to graph this, by the way, ladies and gentlemen. Okay, but what I first have to introduce to you guys is the idea that this here is r is a function of theta. And that curve called a cardioid, a heart, if you want to think of it that way, because that's where it comes from. This is very easy to describe in the world of polar coordinates. R is 1 plus sine theta. But if you said, I don't want to learn anything about polar form or polar coordinates or polar curves, right? Because this is in the world of polar now. I want to go back to rectangular. And I'll say to you, not advisable. Now, here's why. Let me see if I can do something here for us here. Right? So, in case you guys didn't know, here's why. What I'll do here is r is 1 plus sine theta. I'm going to multiply both sides by r. And if I do, I get r squared is r plus r sine theta. So all I did was multiply both sides by r. Now on the left, you might say, I know what r squared is. And I'll say, I know. It's x squared plus y squared. And on the right, you might say, what's this? R sine theta. So what's r sine theta? That's the y variable. So here's y, and then here's x squared plus y squared. And so altogether now, you get x squared plus y squared is r plus y. We can subtract y from both sides or move it to the other side. We get x squared plus y squared minus y equals r. Okay, and then I can say to you, we're going to square both sides now. And on the left side, I still have x squared plus y squared minus y to the second power. And then on the other side is just going to be x squared plus y squared, because that's what r squared is. So here's an equation here. And it's in terms of just x and y. So you have x squared plus y squared minus y to the second power is what you see right here. So this is in rectangular coordinates. And here's my point to you. Here's why I'm starting this as a discussion. I always use this version here to show students that what you see here in terms of x and y is a lot more complicated. I'll say this is more what? Complicated. And because this is a more complicated way to describe the cardioid curve, the polar version right up here from the beginning here is just 1 plus sine theta. So if you had to learn techniques in graphing with the Cartesian version, that would be a lot more complicated, a lot more elaborate, might even be impossible. Here's what I'm saying. They're going to say to you to graph this, right? And you're going to go, oh my God, I can't graph that. There's no technique. It's not a parabola. It's not an ellipse. It's not a hyperbola. It's not a line. It's not a trig function. You got to convert it to polar. You say, what's the conversion? Well, you'll see that this curve is really 1 plus sine theta in polar coordinates. And not just that, the graph of this 1 plus sine theta, if I go to my browser here, is what you see here, right? It's a cardioid, it's a heart, polar curves. The reason I bring this up here is because, you know, in later courses, you take things that exist in the polar world. It's easier to work in the polar world than it is in Cartesian. 1 plus sine theta. And on this worksheet, I have a bunch of other curves. Here's another cardioid, by the way, but it's a cardioid that's on a side. And you say, this is 2 minus 2 cosine theta. How do we convert that? Well, there's a way to convert, just like what I just did. And here's another shape called a limicon. That's not a circle. It's a convex limicon. R is 3 plus cosine theta. So these are some examples of polar curves that exist. You know, 3 plus cosine theta. You might say, well, how do I graph that? We're going to learn how to graph that too. And then I got another 5 minus sine theta. Notice that's not a circle. The top portion is fatter. The bottom portion, the top portion is thinner and the bottom is fatter. So you got all these curves that exist in polar written 5 minus sine theta. And that's easier to describe than if I said to you, guess what? You know, how would that look? You know, if I wanted the iPad, by the way, the limicon that we just seen was 5 minus sine theta, right? I want to point out R is a function of theta. So if I had to describe this in terms of Cartesian coordinates, it's the same procedure. Multiply both sides by R, and you get R squared will be 5R minus R sine theta again. And R squared, we know, as x squared plus y squared. And R sine theta is just y. So you can add y to both sides again, and now you get x squared plus y squared plus y is 5R. And what you'll do here is square both sides, because this is the only tools you have. And you'll get x squared plus y squared plus y to the second power is 25r squared. And at this point, replace your r squared now with what it is, x squared plus y squared. So here you go. X squared plus, what did I have a 2 on? No, that's y squared. Let's get rid of that. So x squared plus y squared here plus y to the second power becomes 25 x squared plus y squared. And this is the rectangular version of that curve. In other words, if you had to learn procedures to graph something like this, you know, it would be time consuming. Now, r equals 5 minus sine theta is a lot easier to handle than the Cartesian version, which you guys see here. So this is why this system exists. And then if I go back to the browser here, we have various curves known as roses, and they're described as r is cosine 2 theta or r is sine 2 theta. So we have what's called a 4-leaf rose. You know, if you had to learn and you said, Mr. Judge, that's 4 leaves. That's not a parabola. It's not a circle. It's not a hyperbola. It's not an ellipse. It's not a circle. It's not a line. You know, I only know how to graph those things. Well, guess what? When you take a trig course, you learn how to graph other things. That's part of the course. So you could graph roses. And you have a 3-leaf rose. So we have various curves. You have lemniscates. The infinity symbol is a lemniscate, ladies and gentlemen, technically, and it's r squared is 4 sine 2 theta. R squared is cosine 2 theta, another lemniscate. That's your infinity.
To infinity and beyond.
So as you can see, we're pretty serious about graphing polar curves. But you first have to understand and learn that, wow, you know, that using these tools that we have x is our cosine theta, y is our sine theta, x squared plus y squared is r squared, tangent theta y over x. All of these tools are used here to go back and forth from polar to rectangular. And you can now describe curves that were much more difficult in the past. And so now we want to look at converting curves. So these are converting curves. So the first part would be to convert, and this is converting curves. Convert things that are, convert the equation to polar form. And there's a lot you can do when you say convert this equation. This is what they mean if you have x squared plus y squared maybe equals 4. Now, what you guys should know is that's a circle. Radius is 2. Centered at the origin. That's intermediate algebra. Okay, this was r squared. Remember that? So, I mean, I talked about that, in my intermediate algebra course. We're graphing circles, finding the radius and the center. And so when they say convert this equation to polar, well, polar, if I can get the right tool, and polar form, you're talking r is f of theta. It's a function of theta. Now, this is a very simple thing to do. I'm going to use this relationship. If you said, all I have to use here is some of the concepts that we've had before, meaning this means that x squared plus y squared, this is represented by r squared. We were using that in our conversion last week. So that means r squared is 4, ladies and gentlemen. Do I just looking at this r squared? And now here, r will be, if I solve for r, plus or minus the square root of 4. R is going to be plus or minus 2. Now that means two things. R is positive 2 and r is negative 2. Now we have to be kind of careful with something like this, just so you guys know. You're careful because of the fact that even in rectangular coordinates, r is defined to be positive, but in polar, you can have negative radius values. And this is where r equals f of theta, where this is a constant. So r is a constant. And we already know in rectangular what this is. This here is a circle. If we get the right tools, a circle. Radius is 2, centered at the origin. And that's in the rectangular coordinates. But in polar, we can use r as 2 or we can use r as negative 2. And this is constant. So that will work for any theta value, by the way. Now, let me show you in Desmos. Now, Desmos is a very good graphing calculator. I use this here to show people that, I think it does it in polar too, r equals 2. And that's a bit odd. I think it's because it's not to scale. And I'm going to say 0 to 2 pi. I don't have to restrict the domain, but 0 to 2. I think if I start spelling pi, yeah. Now, you might say, Mr. Judge, that doesn't look like a circle. And I'll tell you, look at the x and y axis. They're not, isn't to scale. So I have to figure out how to make that to scale. R is 2. You guys see what I'm saying? It's like, here's from -1. It looks like it's an ellipse, but we got to convert this to scale. We got to change that. It's probably in the settings. How about if we go the same? There should be a really good. How about -2 to +2? -2 to +2. There we go. Now, the x and y, it's to scale. So the distance between, points on the x-axis and the y-axis are now the same. So this is the value r is, let's do 2. And that's what we're talking about. That's a circle centered at the origin. Radius is 2. And ladies and gentlemen, if I just do this, r can be anything. R could be 5 in my polar coordinates world, and that's going to be a circle. So I can change the radius values all day long. As you can see, what happens there would be simply, and I could go back here if we can edit that. Yeah, R could be whatever, let's say 10. And I could do that all day long. We can change the size, the radius. It's still centered at the origin. And that's the equation of a circle. R is a constant in polar form. So we have to be aware of that. We can generate any circle in polar form by just using R as a constant now. All right, let me just do this one here. You say, what about the negative value of R? Let's see if Desmos knows about those negative values. Mr. Judge and his calculus students know about them. All right, where's R? R, let's say, is -2. Get rid of this one. So in purple, ladies and gentlemen, as you can see, even if R is negative, it's still a circle because we can have negative radius values in the polar world, not rectangular, but in polar we can. So if you're going to convert to polar, R is negative. That's allowed, remember? R can be negative. So I want to show you guys here that they're the same curves. R is on top of green. Anyway, I think that's fascinating. So to let you guys know, I want you to note, that whenever R is a constant, that's a circle. Centered at the origin, radius R. So you know. Anytime you have a circle. So you might say, okay, Mr. Judge, what about this next one? If you have the Cartesian coordinate y equals x, what does that look like? And I'll say do some algebra here. You guys know this is a line, by the way. It's a line through the origin where the slope is 1, right? Y-intercept is 0. The b value is 0. So you can graph that, by the way. And you might say, what about the polar version? Say, what about polar? Well, doing some algebra, you might say, I'm going to divide both sides by x, and I get y over x is 1. So using some algebra, we know, what was tangent y over x? Using all these facts here to begin with, these 4 facts, right? You got 1, 2, 3, 4 of them. Tangent theta is y over x. So you can describe this as, this is going to be tangent theta. So I can say tangent theta is 1. And you say, I know what that happens for. Theta has to be pi over 4, or theta has to be 3 pi over 4. Let's think all students take, 3 pi over 4. So here's kind of something kind of interesting here. This theta is constant. So theta is pi over 4, and theta is 3 pi over 4. This theta value is constant. So if theta is constant, we have lines. There's going to be a line, ladies and gentlemen, through the origin. So we're using our trigonometry, and let's see if we can actually find that. And we'll now say theta, and I don't think it has the Greek letters, does it? Maybe if I spell it out, theta. Okay. Yeah, theta equals, now I have to spell it out, pi, and you say divided by 4. And I'll have to look it up. Yeah, I think there's a way to do this. I think Desmos has an issue, but some of the others don't. But anyway, nevertheless, this is a line. Theta is a constant. So I'm going to let you guys know as a fact, not just any line. Theta is a constant, is a line through the origin. And yeah, I think there's an issue, and I have to go back and double check in Desmos. I think other software programs can do that. Like I think the graphing program, let's double check Grapher in Apple. Excuse me. Let's see if it does it. And you might say, oh, it's not there. Let me do this. How about this? You guys don't see that. If it works out, I'll show you. So I'll say theta equals pi divided by 4. Yeah, but it's interesting here. Okay, let me show you guys here. So I'm going to go to, well, I'm going to say this is a TI, but it's not. I'm going to send it to a source. No. I'm going to send it to Grapher as a source. There we go. Now I entered, this is with something called Grapher in, Apple puts a free graphing software, and that's theta is pi over 4. So notice you do have a line, but it doesn't have the complete line. The line has to go through the origin. So it's kind of odd that even in Grapher, it doesn't graph completely correct. Okay, to let you guys know, even Grapher doesn't do it correct. That's interesting. And so does Desmos. So it just shows you that technology, you can't really rely on technology, even though people think, they can. If I said to you, guess what? If you had to graph this curve in the world of polar coordinates, you would simply know it's a line with an angle pi over 4, which is 45 degrees. So here's really this is theta is pi over 4. So you have these lines in the polar world. Here, don't forget, you got your pole and you got your polar axis. And, we can emphasize that. And this angle, positive pi over 4. So you got lines in the polar world, and that's how it would be graphed, really. Just like you have circles, you can graph circles. So you can graph circles and lines. And I always start off with those very simple facts, circles and lines. Your book kind of is interesting. It gives you circles and lines. And then your book says, okay, here's another example. I'm going to kind of make that up. What if they say y equals, I don't know, x squared here in the book? Let's double check this. All right, y equals x squared. Now we're going to have to describe this in polar. You guys know this is a parabola, by the way, centered with the vertex. Vertex is at 0, 0. So these are curves we know from algebra. What is it in the polar world? Well, here's what you do. We know what y is. We know what x is. Remember, what is x? R cosine theta. And y we know is r sine theta. So we're going to substitute these variables here. So you have r sine theta will be r cosine theta to the second power. Now, using a little bit of algebra, we get r squared cosine squared theta, because that's the definition of squaring. And one of the r's cancels. So you have sine theta is r cosine squared theta. Now, like before, we solve for r here. So you want to solve for r, like sometimes you want to solve for theta if you can. So we can solve for r, and this means r will be sine theta over cosine squared theta. Okay, and now here's where we use some identities here. Remember, cosine theta is squared theta is cosine theta 1 over cosine theta. So, we did solve for r, but we can actually write this a lot more elegantly. Since we know about identities, we studied that. Sine theta over cosine theta is tangent theta, and then 1 over cosine theta. We can write what that is. So we know that's secant theta. So here's my polar version. We got a polar version here. And let's go to, if we can, oh no, we don't have to go there. We can tangent theta, secant theta. So let's go to Desmos. Let's see if Desmos is sophisticated enough, because look at that. It can't even draw a line in polar. So if we go to Desmos, let's see what this might be. This will be r equals, I think we said tangent theta, secant theta. It has a tangent curve function there. Let me go back, because it has tangent. Here's my functions, tangent. Misspell. Don't misspell tangent. Don't misspell theta. Jeez. What's going on here? Wish they had a Greek letter there. Theta. And then you have the secant curve. So, good. We have secant, now theta. And I think something's bothering me. Yeah, oh, take a look. It's not bothering me. This is the polar version, ladies and gentlemen. R is tangent theta, secant theta. But you already know that in rectangular, it was this. So it makes sense. It should have the same graph. This is y is x squared. Okay, so it has the same graph, and it makes a lot of sense, because if I said to you, y equals x squared, same exact graph right on top of each other. Evidently, red and blue make purple, so if you can see that there. Yes, ladies and gentlemen. So, so you y is x squared. Now we can write this in polar. Now you might say, but I thought you said, Mr. Judge, this makes life easier. And I'll say it does, but they're trying to get you comfortable with sketching curves, to let you know. And you might say, what about something like this? Another example. You can say x is 2, and you want to know what this curve is in the polar world. right? Well, substitute. What was x again? Right, x is r cosine theta. So we know r cosine theta is 2. And I can solve for r. I get 2 over cosine theta. And we know this will be 2 times 1 over cosine theta. Use your identity. That's r is 2 secant theta. So this line here is actually, if you guys remember, that's going to be a vertical line from beginning algebra. It's a vertical line. X is 2 secant theta. And then similarly, you might say, what if we have a curve like y is 6? Remember, this is rectangular. It's going to be, this is a horizontal line, by the way. You're going to do the same thing. You're going to replace y with what it is in terms of polar. This is r sine theta. So we have r sine theta is 6. We can solve for r. R is 6 over sine theta. And at this point, you guys may know that that means r is 6 cosecant theta. So this is a horizontal line in the Cartesian world and a horizontal line even in polar, because it's the same curve. So they're just trying to get you kind of comfortable and used to these ideas that these are curves that you might have seen. And then I might say to you another example here of, yeah, how about this? If they give you, sorry. How about x squared minus y squared is 1? And you might say, I know what that is. That's a hyperbola. What does that look like? Well, replace x and y with what they are in the polar world. This would be r cosine theta. Don't forget to square that. Minus r sine theta. Don't forget to square that. Equals 1. So you get r squared cosine squared theta minus r squared sine squared theta is 1. You can factor out your r squared. You got cosine squared theta minus sine squared theta is 1. And so you'll have r squared going to be 1 over here cosine squared theta minus sine squared theta. And right now you might say, I think this looks familiar. There might be an identity here that you can use. Remember, this is a hyperbola, right? So if you go to your list of identities, let me do this here. Let's go to our list of identities. Yeah, here we go. I'm going to go to the website. I know this is polar. Let's go to the browser here. So I want to show you what you guys have here. I think you have your identity sheet, right? It's the same thing on your website. You might say, I've seen cosine squared theta somewhere. You can use, you got a couple of options. You can say cosine 2 theta. So I might be tempted to say here, if you guys can see that. Let's go down here to the double angle identities. Yeah, cosine squared theta minus sine squared is cosine 2 theta. So, I mean, I think you could use that. And 1 over cosine 2 theta, let's ask you guys here, what do you think? We can say r squared will be, what's the reciprocal? Is that secant 2 theta? Okay. And we can actually, you can even leave it like that if you wanted. This nice hyperbola. Anyway, we could leave it like this. R squared is secant 2 theta. Anyway. So I'm wondering, how does an ellipse look like? General form of an ellipse. Let's note. You got x squared over a squared, right? Plus y squared over b squared is 1. So if we convert that, focus on this x coordinate and the y coordinate. We're going to convert this. Remember, that now gives you r cosine theta squared over a squared plus r sine theta squared over b squared is 1. And you'll get this r squared cosine squared theta over a squared plus r squared sine squared theta over b squared is 1. And we can factor this out. You got r squared now. Now be careful. Cosine squared theta over a squared plus sine squared theta over b squared is 1. You may have some issues here with this. I should say, how about, let's do some multiplication here. So r squared will be b squared cosine squared theta plus a squared sine squared theta over this a squared b squared is 1, which means my r squared will be 1 over, this whole thing. Or let me do this. R squared will be a squared over b squared divided by b squared cosine squared theta plus a squared, sine squared theta. And I'm leaving this in the form of like a relation where you have r squared and it's not really r. And I want to put that the same level here, if I can, graphically. So you do have various versions here of polar for some of these curves you guys know and love. But anyway, yeah. So I'm just going to kind of leave it at that. There's a little bit more that goes on here, but this is not what your book wants to get into in terms of this detail. This is a heavy-duty detail. But we can do the reverse. In other words, they can give you a polar. Like, let's say r is 4. Here's a polar curve. And then they can say, what's the Cartesian coordinate? Or rectangular coordinate version. That's either going to be a function or a relation. And so you have to do the reverse now. So they give you r as a constant, so you have to go in reverse. You say, how do I do that? Well, you know r squared, if you square both sides, you know what r squared actually is. Square both sides. This portion here is going to be now, x squared plus y squared. So you'll have x squared plus y squared equals 16. And then you recognize, oh, you're done. You say, how do you know you're done? Because you know the equation of a circle. This is a circle centered at the origin, radius 4. And that should make sense because we already covered this idea that the radius is 4. So it makes a lot of sense there. So I say, okay. So we got r as a constant. And then if they say to you, okay, another example. Theta is maybe, I don't know, pi over 6. you know this is going to be a line through the origin. But you're going to have to use the tools you know about for rectangular or for polar coordinates. We can take tangent now of both sides. And you get tangent theta, and you say, what's pi over 6? Well, remember what this is. Pi over 6 is, what was that, 30 degrees? So you're going to have to remember your 30-degree triangle. Okay, so here's 2, here's 1, here's square root of 3, here's 60, and here's 30. And so this means tangent theta will be on the left side. On the right side, tangent 30, we know the definition of tangent is opposite over adjacent, which is square root of 3 over 3. So you have tangent theta being the square root of 3 over 3. We need this in rectangular coordinates, x and y. So the definition of tangent theta here was y over x. So you replace this tangent theta with y over x, and you end up with y over x being the square root of 3 over 3. You're almost done. You can solve for x by multiplying both sides by, solve for y, multiply both sides by x. So you get the square root of 3 over 3x. So this, sure enough, is a line through the origin. The slope is square root of 3 over 3. So yeah, you could go back and forth. Just use the appropriate, conversions. If you're going from polar to rectangular, you're going to use the tangent theta, and you're going to use the, you're going to use the appropriate conversion format, right? So you're going to convert again now. They're going to give you a polar curve. And this is kind of interesting. They can say r sine theta is maybe 11. And this is kind of simple. You say, well, what do I have? What tools do I have? I know that this r sine theta, that's my y variable. This is y. So we use r sine theta being y. So you're going to use these tools that we started with here. Way back up here. You use these 4 tools in algebra. Ooh, we've done a lot of work. These 4 tools here. Y is r sine theta. X is r cosine theta. You're going to use these tools here. So, they're just trying to show you that these curves, in rectangular have a polar form. And then again, that's going to be a horizontal line, by the way. And then similarly, you might say, what if they give me r cosine theta is 7 here? I'm going to remind you that r cosine theta is the x variable. And that means x is going to be 7 here. That's a vertical line through 7. R squared is tangent theta. Okay, we have to convert. So you know what r squared was. You're going to substitute. That's x squared plus y squared. And then you know what tangent theta is. That's y over x. So it looks like we have the following. X squared plus y squared is y over x. And if you wanted to solve for y, you have to multiply x to both sides. So you get x cubed plus xy squared. Just multiply x to both sides. So ladies and gentlemen, here's a very interesting curve. I'm just thinking about in Desmos, if I went to Desmos, by the way. And get rid of this, get rid of this, get rid of this. Said y equals x to the third power. Get out of there. Move out. I think that was plus. Is that plus xy? Let me double check. Xy squared. All right, that's a nice. Bet you never seen that curve before. I know I never have seen that. X cubed plus xy squared. So if you were to do this in polar, it's the same exact curve. So, wow, I like that. I like that. X cubed plus xy squared. Nice curve. Okay, let's see if we can do some more here. What's our time like? How about r equals 1 over sine theta minus cosine theta? Okay, I'm going to say to you, remember this is a proportion. Equal ratios, we can cross multiply. I think I want to use a highlighter though. So we'll get r sine theta minus cosine theta is 1. And if we distribute, r sine theta minus r cosine theta is 1. Okay, just distributing here. So you just have to recognize r sine theta and r cosine theta and substitute. You say, what do I substitute? I think this is my y variable, my x variable. So y minus x equals 1, or y is x plus 1. This is a line, ladies and gentlemen. Slope 1 and y-intercept at 1. Interesting. Not too bad. All right, let's see some more examples here. How about r is 1 plus cosine theta? I think that's going to be the cardioid again, right? I'm going to multiply both sides by r. R squared is r plus r cosine theta. So I have two substitutions to do. R squared, r cosine theta. X squared plus y squared. And this is just going to be the x coordinate. So x squared plus y squared is r plus x. So subtract your x from both sides now. And you get to square the r. Or I should say you get to square both sides. And you knew that here, so r squared we know is going to be x squared plus y squared. So this is a more complicated shape. This is a Cartesian coordinate version of whatever this is. R is 1 plus cosine theta. And I'm trying to remember if that's going to be, if we go to Desmos, is that a cardioid? It might be. So we say, where's our letter R? Equals 1 plus, let's get our trig functions, cosine theta. Yep, it's cardioid. Cardioid on the side, on its side here. Yep, recognize that as a cardioid, as a heart. We'll see some of these in our future. And now we try r is 2 secant theta here. How about something like this? It's a cardioid, by the way. So now I have r is 2 secant theta. Well, I'm going to start to write this as something I'm familiar with. And then I'm going to cross multiply, I think. Right? I think we're going to want to cross multiply. This is r over 1. So if we cross multiply, think of it kind of as a proportion here. And, you know, before I do that, I'm showing too much detail, but it's always good. So we'll do this and we'll cross multiply. So we're converting. And you say, why would I do that? Because take a look. You get r cosine theta. We know what that is. That's going to be x. So we recognize this as a variable x. And all that means is this whole expression was the line x is 2, which is vertical. Vertical line. Secant theta is 2. We do the same thing. 1 over cosine theta is 2, and it's 2 over 1. Let's do this cross multiplication here. And it looks like we're going to get now 1 is 2 cosine theta. Or maybe cosine theta is 1/2. And so you might say, what does that mean? Theta is, if cosine theta is 1/2, theta will be plus or minus pi over 3. If you guys remember, you're going to have to draw your right triangle again. Theta definition is adjacent over hypotenuse. That's the square root of 3, right? So this is what we're trying to consider. 1, 2. Oh, that's 60 degrees. Yeah. And all students take calculus. So anyway, right, if we said theta is pi over 3, we know tangent theta is now tangent pi over 3. We need the rectangular coordinate version. I know what tangent, it's y over x. We know this one. So that's what we need to get, y over x. And tangent pi over 3 then, if I write it down here, y over x will be, what's that tangent here, pi over 3? So use the definition. Adjacent over hypotenuse? No, opposite over adjacent. I apologize, not awake. Square root of 3 over 1. And I could multiply both sides by x. So I get the square root of 3x, ladies and gentlemen. But this was plus or minus. Remember that? Because all students take calculus. Yeah. Cosine's positive. Let's go back. All students take calculus. So we had cosine theta being, you see, cosine theta is 1/2. So that happens for pi over 6 over here. 30 degrees? Yeah, here's what we're talking about. Okay, this is pi over 3. This is also pi over 3 because this is the quadrants where cosine is positive. Yeah. So, same thing there. If we say negative pi over 3, and then you take tangent of theta is tangent of negative pi over 3, or replace what you know tangent is, y over x. So you got y over x, and then I'm going to use the even and odd function. I'm using everything we studied, ladies and gentlemen. Tangent pi over 3, we said was square root of 3.
back up here, square root of 3 over 1. And so solve for y, and you get minus square root of 3x. So really there's two answers here. There's two lines, by the way. Plus or minus square root of 3x. Two lines of the origin where they have opposite slopes. Because cosine theta has two answers. One in quadrant 1 and the other in quadrant 4, meaning you had to determine what theta is. And once you find theta, you find tangent theta, and tangent's y over x. That's the idea. You know, so there's some really nice equations. Let me do another example, last example for you guys here. See what I would look at this one here. This is cosine 2 theta is 1. Get you guys to think of that one. I'm not sure. See what our time's like. Yeah, 2:41. Okay. All right. Let's give you guys a few minutes to try this one out yourself. Let's see what you guys get. Where's our clock? Try this one for yourself, ladies and gentlemen. See what you get. So let's find this one here. Oh, that's not what I want to look for. Where is it? Where is it? Where are you? No, I don't want you here. I got to delete, don't save. Let's find this here. All right. See if you guys can see this. I got to dig up everything. So, cosine 2 theta. Maybe, okay. And let's see. I can't see anything. See if I can remove this. What curve is this? Let's see if we can remove these axes. I really have, where is this? Preferences. So I really don't like these. I want to go to preferences for graphing. Nope. Format. Okay. Coordinate system, axes and grids. Polar. Yeah, I got rid of everything. Okay. Guess that's not the way to go. All right, double check, ladies and gentlemen. Let's look at this here. Yeah, got our sound back. Anyway, we got this x is 0 here for this, and that kind of looks like what we're doing, but I have to question that one. I want to do it another way. So anyway, double check, ladies and gentlemen. Looks like the algebra is okay here. Cosine 2 theta is 1. But, you know, come tomorrow, we're going to start to graph some of these here. So I wanted to get you guys started on this. This is going to be homework 5 now. So for homework 5, you're going to do section 8.2 now. And I had the page. Um, 33 to 60. Okay, all. And this is going to be start of homework number 5. So if I say to you guys, I'm going to show you here, I'm going to update your homework in Canvas now. So if I go to the browser, we just have to find Math 241, the assignment, homework 5. So we're going to add homework 5 here. So what you guys can do is get started on your test 4 and homework 5. This is from the book. This is 8.2, and we said 33 to 60 all. It's working with these curves the way we did today. So we're working on these curves, and that's going to be worth 20 points. Okay, of course, that's due the day of your final. And you might say, when is that? Okay. You guys' final, again, if we look at the schedule, right, is on the 15th at 9:30, I guess. 15th at 9:30. So we can say 15th, 9:30 a.m. 15th at 9:30 12:30 a.m.
So there we go, ladies and gentlemen, that, there's a relationship between the Cartesian and polar world. They go hand in hand, and the idea is that the polar world makes everything a lot easier for you. And you might look at this and say, no, it doesn't. It makes it harder. Well, you first have to get used to some of these representations, and come tomorrow, you're going to see what I'm talking about. Anyway, okay, you guys, you have a great day. Just print your name in the comment section. We'll see you later. I'll send the office hours information out to you guys, and take it easy. And you guys have a great day and get to work on this stuff. Okay, so this is going to be also on your final. So have a great day and take care.